have the chance to do the second keynote presentation at the 16th International CAN Conference. And actually, I originally thought that I would like to give a presentation, and I was thinking what could be of interest as a general presentation, and this is perhaps the discussion we have. On the one side we have CAN, but we have a lot of discussions about Ethernet, about industrial Internet of Things. So just to have a look how these two things might merge together, or how do these two things compete. And when the program committee has then done the work, Holger called me and said, I have a good and I have a bad news for you. The good news is your presentation is selected, and the bad news, it's the second keynote. So thank you, Holger. Okay, what I would like to do, I also would like to go a little bit back into history when CAN was invented, and then having a look at Ethernet. Why is Ethernet used? What are the advantages, disadvantages? Then also having an outlook on CAN-FD, and also how this relates then, or what is IoT when we are always talking about IoT. So let's start with looking back into history. So when CAN was born, it was in the 80s, more or less in the early 80s. I think there are still many of you here in the audience remembering the 80s, the wild time. I finished studying in 86, no, in 90, but I started in 86 after serving in the army. So it was the time when we had the first personal computers from IBM coming up. So it was really that everyone could have a computer on his desk. We had the first wearables at that time, much larger than we have today, but I would say the Walkman from Sony, this was one of the first wearables that we could have. Or also remembering the mobile phones. Already in the 70s there have been some mobile phones, but they have been quite tricky. So in the 80s we had then the so-called CNET, and there we really had the first portable mobile phones at that time coming up. So it was a decade of fast evolving and spreading technology. And not only in that areas, also in the areas of automation and inside cars, inside the automobiles, of course. So when looking into automation, we have the automation system consisting of a controller, consisting of I/O devices, of drives, and they need to be interconnected. So instead of having dedicated cables, already at that time we had a kind of a network, but the networks have been based on serial communication interfaces, either based on RS-232 or as a kind of a bus system already based on RS-485. But we had some disadvantages with the serial interfaces, and they have been limited in bandwidth, limited in the functionality, and also limited in the number of devices that can be connected to a network. So this means, or this imposes then, that some of the major automation suppliers at that time started to develop own kind of networks, the so-called field bus networks. So new field bus technology came up during, or was invented during the 80s and showed up during the second half of the 80s, like for example Interbus from Phoenix, or Profibus more or less from Siemens, and Circus, the first Circus interface, for example. And the common denominator of all these new field bus technologies have been still based on the serial communication principle, but the speed was considerably increased in these networks compared to the standard serial interfaces. The networks, how they have been designed and also the protocols that have been implemented provided more features, like for example device management, and basically all of them have been working based on a master-slave communication principle. Looking into the cars, so also inside the cars we had more and more electronics coming in. So we had more and more so-called electric control units inside the cars, which have to be interconnected. And having all these connections in between the ECUs and also connecting the ECUs to the sensors and actuators inside the car, this would have meant that we have much more cables inside the car, and the negative effect of this is then the weight that is brought into the car. So not a good solution to have a dedicated wiring between all these additional electronic units. So this means looking into a car, we have a different or a special situation compared to the automation networks. And this means basically we have a more chaotic communication structure, because when we have a car, we have different functions inside a car that are placed in different areas. So it's not really that we have a kind of a machine which is more in aligned technology. So it's a real mixture inside the car. We have the steering wheel with a lot of interfaces to operate the car. We have the roof with some rain sensor, light control, sunroof that is moving. We have the seat that can be moved. We have the door and all the equipment inside the door. We have the engine that has a lot of electronics around all the mechanics that is inside the engine. And for example, we have a climate system. So all of them need to interact somehow all together. And then the electric world inside the car is not as stable and clean as in the automation world, I would say. So we have a lot of more interferences inside the car, especially from the engine. And what is also important related to the weight of the cables and of the car is that shielding inside the car needs definitely to be avoided. So this means that all the automation communication technology that existed during the 80s already, and also the upcoming bus systems, they are not really applicable inside the cars. And consequently, communication strategies and also technologies need to be invented new for the car. So a new approach was necessary. And in the early 80s then, a team at Bosch were the first to investigate the possibilities that have been out there in the market, and more or less came to the conclusion that we need to have something new inside the cars. And basically then in 1983, Bosch started the development of the new serial communication system, and in 1986 the control area network was presented the first time at the SAE Congress in the US. And then already 1 year later, 1987, the first CAN controller chips have been available. This have been the from Intel, the 82526, the so-called full CAN controller, and only a few months later we had the 82C200, the so-called basic CAN from Philips Semiconductor. And what was now so special in CAN, what other communication systems did not have? And the special features from CAN, these came really out of the requirements that have the use inside the cars. And I would like to highlight here 3 of them. First of all, the bus access and arbitration principle that is used inside CAN. It's the carrier sense multiple access with collision avoidance. So carrier sense multiple access is a mechanism that was already existing at that time because Ethernet is using the same mechanism. This means every node in the network is listening to the network, and when no transmission is ongoing inside the network, then the node starts to transmit its message. But of course it can happen that then there are several nodes who identify that the network is available, that no transmission is ongoing, and then start to transmit their message. And this means that we have a collision on the bus. So this is the typical case with Ethernet, because in Ethernet it's not CA, collision avoidance, it's collision detection. So Ethernet, the device then recognizes, oh, there's something wrong on the bus, backs up, and then each node that has transmitted at that time draws a random time, and it has to wait for the time until it retries the transmission again. And if you have many nodes in the network and you have a higher bus load, so that a lot of transmission shall be ongoing, then this more or less causes more and more delays inside the network for the nodes who want to transmit their message. Inside CAN, it's completely different, and I think all of you know how CAN is working, that we have this bus arbitration based on the CAN message identifier that is transmitted in the beginning of each message. And so every node can start, and every node is listened to the message, and as soon as the node is recognizing that not his value he's transmitting, the bit the node is transmitting is on the network, the node is backing up and is starting to receive immediately. So it's really CAN avoids collisions, and also based on this message identifier, it's an inherent message priority. We also have a prioritization of messages. So always the highest priority message wins the arbitration. Then another special feature is error signaling and error recovering. And the arbitration only works because we have this error signaling and error recovering mechanism. So every node immediately starts to receive the message, and then we have special conditions inside the message. So we have some certain frame delimiters. So these are bits that have to be always a static value. If this value is not seen, a node can say, oh, this message is wrong, and then starts to transmit a so-called error message, which more or less deletes or destroys all the remaining part of the message that the transceiver is transmitting. Also, the receiver recognizes this because the transceiver is doing a bit monitoring, also checking if the value the transmitting node sets on the bus is visible on the bus. And on all nodes in the network, the message is destroyed, and then a new arbitration phase is more or less immediately started. And this mechanism ensures data consistency on all active nodes. Also, of course, we have a checksum at the end of a message. Also, if some node detects that the checksum doesn't match to the content of the message, then also the message is destroyed on all nodes and it's retransmitted again. So CAN always ensures the data consistency on all active nodes. And the third one is the physical layer. So the way how ones and zeros are represented on the bus line. And as we have this differential signals on the bus, where 0 voltage with CAN high speed, 0 voltage is the recessive bit, so more or less is the passive state on the bus. And then we have a difference in the two lines with 2 volts. Then we have the dominant level on the bus. And we have then the 2 lines. And this makes it rather immune, on the one hand, concerning common mode interferences. And if we use twisted pair, so if we have the cables twisted, it's also very immune against electromagnetic interferences coming from the outside. So this is actually, I would say, these are the 3 most important features that CAN provides. Now, as the next part of my presentation, I want to look how CAN made its way into industrial or non-automotive applications. So actually in 1991, we had more or less the first real product on the market that was working with CAN, and this was from Daimler, the Mercedes S-Class. Which was released in 1991. And then in the late 80s and early 90s, already I talked about this, we had the classical field buses coming to the market. They have been introduced by the large automation companies. And so we had on the one side the large automation companies with their own proprietary solutions, and on the other side we had with CAN, mainly large companies in the automotive area. So we did not have a large company promoting CAN for industrial applications. And initially, this was more or less a bit out of the picture, of course, because really the target for CAN was automotive. But since CAN has these nice features, it was very interesting also for the industrial area. And so smaller companies started to promote CAN for industrial applications. And some of them, for example, have been Softing, I+ME, Quasar, or STZP, that really went or promoted CAN for industrial applications. And I just would like to give some examples of first applications that have been done with CAN in the non-automotive area. And these have been applications I was aware because we have done them at STZP. So for example, very interesting, very early we did a cow milking system based on CAN. And we had these stands. Every stand had a panel. So we had information from the cow. We had a weighting system, a feeding system. Everything was controlled by CAN, and everything was then connected to a PC, more or less handling the overall control and also doing the data handling. We had a coil. We had a coil winding machine running with CAN. We had a well, this is not an old, but I wasn't able to find an old picture, but it's a machine for checking and counting paper money that we already did at that time. And we also did an implementation of CAN for an endoscope system. And actually, more or less, the endoscope system is still available to today with the same implementation that we have done in the very early 90s. So what is very interesting here is that these are more or less all applications that are not really factory automation. So we don't see large machines here. It's some other areas. We have here special areas with the cow milking system. We have medical, and we have two other very dedicated machines. So CAN really spread it in the non-factory automation world very, very early. And this was also due to the specific features CAN had provided. And actually, at that time, more or less, CAN was used in a way that we had a dedicated CAN system inside the machine. So it was not really necessary at that time to have this common approach with a common application layer and so on. This was more or less before the time when we started to work on CAN application layer or CAN Open. Of course, there was also a need for CAN infrastructure components, and I thought it might be interesting how one of the first PC CAN interface boards at that time looked like. So it was the ISA bus, and yeah, every components with pins, and it was more or less you could even solder it by hand, which is not possible anymore today. And actually, this was what Holger mentioned on the physical layer side. At that time, there was no real ISO high-speed layer available. So the first implementation have been used in RS485 transceiver chip, but used it in a bit different way. So this had to be standardized more or less, and also the DSAP connector. Everyone had an own pinning on the DSAP connector. So this was why one of the first tasks of CAN in automation was to specify the pinning of the DSAP connector. And also, Holger mentioned Intercama show in Düsseldorf, and here we presented one of the first CAN repeaters at the Intercama fair in Düsseldorf in 1992. But in order to broaden the know-how and also the acceptance of the use of CAN, as it's necessary to have a supporting ecosystem. And an ecosystem consists of product suppliers, consultants, system integrators, and also the customers or machine builders using it. And as we learned in the first keynote from Holger, this requires much more than only system and technology that allows to transmit data. It's necessary to have an application layer with device and application profiles where we have commonly agreed definitions and specifications, and this is really important to have this. And so 1992, CAN in automation was founded, and one of the first tasks was more or less to work on an application layer. So we had in 1992 the CAN application layer. It was that fast because there was a lot of work already available that could be used, needs to be merged, and we had a CAN application layer standard that was already also used by, especially by Philips Medical Systems in Eindhoven in the Netherlands, already in X-ray system, so already a tested standard. But as Holger said, it was not really so comfortable to use this standard, and therefore in 1994 we had then CAN Open, CIA 301, as another application layer standard, which was more easy to understand and also more easy to implement, especially towards the application. And when we look today, what we have today within CIA, we have, so CIA still maintains and develops the most comprehensive set of standards for applications and device profiles. And as we have seen, also other networks have started to reuse this big knowledge and availability of standards like PowerLink or EtherCAT. So I was talking now about the industrial area. When we look into the automotive area, it's a complete different approach they took there. On the one hand, when we are in the industrial or non-automotive area, we have higher layer protocols, we have device profiles, we have application profiles, and also Holger showed that we have a big set of various higher layer protocols that exist today. On the automotive side, especially inside cars, we have a different approach. And the approach is here that each manufacturer specifies a kind of a catalog for each, in a catalog for each data. Actually, the data is called a signal, which ECU transmits the data, and which ECUs receive the data, the frequency of the data, so how often the data is transmitted, the message ID that is used, and also the position inside this message ID. So this is a completely different approach that was taken already taken in the early days of CAN. And today we also have additional common definitions that became available, like for example in AUTOSAR for diagnostic purposes, so that the way how diagnosis can be done on cars is more or less in a common way, so for each different type of car. Okay, now towards Ethernet. Basically, the question, is Ethernet a threat for CAN? Actually, around the year 2000, when we look into the history, Ethernet entered the stage in industrial automation, and already some years before, there was a discussion about using Ethernet in industrial automation systems. And out of this discussion, as a consequence, the first organization targeting common specifications for applying fast Ethernet in industrial automation was founded in 1999, the IIOT. I don't know if someone still remembers IIOT, so it doesn't exist anymore today. It vanished through, I would say, the late 2000s. But then we already had coming up the first real industrial Ethernet protocols, also promoted by the big automation suppliers like Ethernet IP. We had PowerLink version 1, 2003, Profinet and EtherCAT, 2004, Circus 3, and in 2006, PowerLink version 2. And the question is now, why was Ethernet so attractive for industrial data communication? So why was everyone looking into Ethernet? And there are some aspects of this. First of all, since Ethernet is used more or less in all office networks, so there's a huge amount. It's like with cars. We need a lot of CAN controllers because the cars need a lot of CAN controllers, and here with Ethernet, there are a lot of files consumed by components that go into the office networks, and also CAN Ethernet controllers. So the components, more or less, are also quite cheap for industrial Ethernet. Then with Ethernet, we can do large network extensions. So more or less virtually the network can become unlimited. This is what we see today with the internet. Then we have a fast data transmission. So we have with fast Ethernet, we have 100 megabit, and that compared to CAN with 1 megabit, it's 100 times faster. So we have large data frames, so up to 1,500 bytes in one message. And both fast data transmission and large data frames, this gives us a very high bandwidth that becomes available. And also, the number of nodes inside an Ethernet network is also virtually unlimited. So actually, these different criteria made it especially of interest for factory automation. Why factory automation? Because in factory automation, we have large machines. We have the factory floor where all the machines are. All the machines need to be interconnected on the factory floor, so large distances that need to be bridged. And also, since the machines become always more and more sophisticated, we also had more and more higher demands on motion control. So shorter cycle times and also more data to be transmitted. But what about other areas? We're not looking into factory automation, like power and energy, like oil and gas, especially subsea, building automation, elevators, for example, trucks, utility vehicles, farming machines, small machines like ticket machines or gambling machines or handling machines, measurement systems, then medical or laboratory automation, automotive, recreational vehicles, so quite special vehicles, but also a nice market, and also small robots that might be also battery powered because they are mobile. So these facts that apply for the use of Ethernet in industrial automation actually don't really apply to these markets. And why should we stay with CAN in these markets? It's the robustness of CAN that we have been talking already. CAN is a real bus system. So with Ethernet, we have a point-to-point system where we need switches in between each device. With CAN, we have more or less CAN, and we can connect on this a line, and we can connect to this line anywhere where we want. We can even make small stubs. We can also make a star topology, for example. We can even make a daisy chain with a passive connection inside the device, which means that on Ethernet, where we have a point-to-point, if a device is a switch or a device with an integrated switch fails, then some part of the network is lost. That's not the case with CAN. Only the device that has a problem is lost with CAN. We have short data packages with CAN. Typically in the automation and control world, we have control commands that are only a few bytes that need to be transmitted, not that we have to transmit, as with Ethernet, a minimum 42-byte data package, where we might only need a few bytes inside the data package. And this also addresses another thing, power consumption, because with Ethernet, we have the PHYs that have need or have a higher power consumption than a CAN transceiver. We need CPUs that have more performance because we have to execute much more protocol software with an Ethernet-based protocol. So typically, the power consumption is about 3 times higher for an Ethernet-based interface than for a CAN-based interface. Monitoring troubleshooting on a CAN network, as you know, we can connect anywhere on the CAN network where we want, and we see always all the data in the CAN network, and that's not possible with an Ethernet-based network. And it's also the price. So typically, an Ethernet interface, considering all the transceiver, the PHY, the coils, the more performance CPU that we need, we can say that the price is around, for an Ethernet interface, 3 to 5 times higher than for a CAN interface. And even the car manufacturers consider it 6 times higher because of their special way of using doing the Ethernet transmission with broader reach. But also there's a disadvantage, and this is the maximum network extension that we have with CAN. 1 megabit, 40 meters, and if we want to go down to, let's say, or far 200 meters, 250 meters, then we have to lower the baud rate perhaps down to even 250 kilobit. But yeah, still has its existence, especially when these requirements are important. So power consumption, especially for battery-powered systems. So it's really, CAN has a lot of advantages. The uptime, the main time, so between failure, the diagnostic and maintenance capabilities, and also the price. Now looking into CAN FD, obstacles for CAN, we have maximum 8 data bytes per message, and we also have the bandwidth limitation based on the network extensions. We can do some workarounds, like for example, we could use more CAN networks, or we could use other networks with similar working principles if you would like for example FlexRay, which was done in some of the cars by some car manufacturers. But now we have CAN FD, and the improvements with CAN FD is up to 64 data bytes per message, increase of transmission speed after the arbitration phase, so it can go up to 8 megabit per second. We have then a longer network extension at the higher transmission speed, so it's only relevant for the arbitration where we have the lower network speed, which gives us then a larger network extension. And we have improved error detection capabilities, which even reduce the residual error probability. And now looking future of CAN FD in automotive application. Of course, Ethernet came into the cars because more and more functionality came into the car, which required more bandwidth, like driving assistance and security, like camera systems, the surround view that we have today, or infotainment applications. So all these areas required, of course, much more bandwidth than we have available with CAN. So therefore, Ethernet was already introduced in the last decade. And, but also here, there were special requirements that needed special technical solutions, like lightweight cables. So broader reach was invented, which is also the transmission of fast Ethernet over a unshielded twisted pair cable. And also, some of these applications need to have a synchronized way to work, and also a guaranteed time when data arrives at receivers. And therefore, at that time, AVB was used together with IEEE 1588. And in the future, TSN is targeted for this. Also, new mechanisms have been developed in AUTOSAR, like intelligent PDU multiplexing, secure onboard communication, or end-to-end protection profile. So here we also have more data that needs to be transmitted, which is very tricky to do with the classic CAN. And this needs to new requirements also. As I said, more data to be transmitted, larger messages. But also we need to have more data because we need to have authentication mechanisms for securing safety-critical data. So will Ethernet replace CAN in cars? Actually, definitely not. At least, I would say, within the next 10 years. Costs are for the car manufacturers a major concern. And as I said, they calculate about 6 times the cost for a CAN interface. Ethernet is only point-to-point, so this restricts the topology. And we need to have these switches. And unused ports of a switch, these are also a considerable cost impact on the car. So if you have an optional function the customer does not order, the port on the switch is still there. And also the use of powerful CPUs with an MII interface, so with an integrated Ethernet controller, for simple ECUs like indoors is not acceptable, also concerning the price. So therefore, outlook for CAN FD. CAN FD will be the bridge between classic CAN and Ethernet inside the cars. It's the most cost-effective solution. It's well known by everyone at the car manufacturers, and this is a very, very crucial point here. It's very important, but the other way, when Ethernet, there's only always a small team, at least today, who really knows how to handle EtherCAT and what to do, but with CAN there's really broad knowledge today. And also I had some discussions with several of the car manufacturers in Germany, and they all told me that CAN-FD will be in the next car generations, and it will not replace CAN completely, at least in the next car generations. So looking into non-automotive applications, when is CAN the preferred network solution here? It's the cost structure, flexibility, ease of use, and the low power consumption. And this makes it the perfect solution for smaller machines, applications with limited network extensions, or also when we have larger machines where we need to have dedicated subnetworks and extensions to the larger machines. And of course, because of the power consumption, all mobile applications. And CAN-FD even provides more. We have a higher bandwidth, we have shorter transmission types because of the higher bandwidth, and we have longer network extensions at higher transmission speed. And we have the larger messages up to 64 byte. So this makes CAN-FD suitable for even more applications, but on the non-automotive industrial side, we are still waiting on suitable CPUs with CAN-FD. So actually we need to have smaller CPUs, for example, a small Cortex M3, M4 with 2 CAN interfaces, and that's all what we need. Finally, CAN Internet of Things. What is Internet of Things? So actually it's Ethernet, Internet everywhere, but bring it down, it's Ethernet from IT down to sensor level, and integration of automation networks with IT networks and cloud services. So looking closer to this, what are the use cases? It's improving diagnostics, maintenance, and management capabilities on the assets, on the machines. It's optimizing production, making production more flexible. And it's about communication between cars, cars and infrastructure, cars and humans. And when we look to the data that is transmitted, and actually here it's more, again, the automation and control view. When we look to IoT-related data and automation and control data, it's not the same data that is transmitted. IoT-related data is detailed diagnostic data, which has larger data packages, and this is transmitted less frequently. On the automation and control side, we have short data that is transmitted frequently, and here we need to have real time. So we have a defined latency for the transmission. And when looking into IoT and in the Industry 4.0, there are actually 2 technologies that are really discussed as the leading technologies that are used in that area. And this is, on the one hand, TSN, time-sensitive networking, which extends the Ethernet standard with real-time capabilities. The real-time actually can go below the microsecond, but it's always then a trade-off between cost and performance concerning the implementation. So I would say the higher or the shorter the real-time is, below the microseconds, the more expensive the technology will be. On the other hand, OPC-UA, it's a standardized protocol with semantics for each data point. So we already have a lot of protocols, but what is different here compared to the other industrial protocols is that typically the industrial protocols transmit the data, and the transmitter and the receiver, especially the receiver, need to know the meaning of the data. With OPC-UA, the information is given from the protocol. What kind of data is transmitted? What is the information that is transmitted? And also OPC-UA supports security mechanisms like authentication and encryption. So will IoT go down to the field level? When we look to the field level, there we have several properties. We have automation control data, so short types of data transmitted often. Here we are quite cost sensitive. We need to have high reliability, and we need to have maintainability. So Ethernet is not always suitable in that area. And here, actually, CAN is a preferred solution. But when it comes to IoT and the use cases, we also want to transmit extended diagnostic data from the devices in the field. And here CAN is not suitable because we only have 8 data bytes per message. But CAN-FD here can solve the problem. Now looking at an IoT architecture with CAN-FD, so for the people sitting in the back. It's perhaps now too small. But here we have the machine level, and inside the machines. So this is the area where we still could have CAN-FD for the machine communication, real-time communication. But then on the next level, we can have in the interconnection of machines and for getting all the data out from the machines, we can have already OPC and TSN with Ethernet, and that could go up to the ERP level or the IT world. So finally, CAN-FD is the perfect subnetwork inside a machine for IoT-related applications. It handles automation and control data, but in parallel, it can also handle IoT-related data. And since we have CAN-Open or CAN-Open-FD, which is also used by several other industrial protocols, we already have a way how to combine everything. And as Holger mentioned, there's already a working group working on CAN-Open and OPC UA, and also downstairs you already see a CAN-Open-FD demo network of different suppliers. So overall, if we would use CAN inside the machines, then we would definitely have an overall cost saving. Finally, now the conclusion from my side. Will Ethernet become the only communication system used for automation and control purposes? I would say definitely no. CAN or CAN-FD in the future remains unbeatable when it comes to cost level, ease of use, reliability, and flexibility. Tick off. CAN-FD comes exactly at the right time to make CAN fit for the future. And CAN-FD is a perfect subnetwork inside machines for IoT-related applications. Thank you.
Thank you, Mr. Schlegel, for your sharing the experience with us. So again, up to you, the time for questions. Please raise your hand. Please, Mr. Leonardson. Mr. Leonardson, could you please take the microphone?
Perhaps you need to switch on.
I'm going to assist you.
Yeah.
Yeah, you said one of the advantages in CAN was the arbitration and the error handling. I would say also that the whole communication controller is included in hardware.
Yes.
So even if the software stops working, the communication is still working. And especially that's important, of course, in the bus structure, where if some nodes gets lost, it's still, the communication is still working.
Actually, when you address the bus structure, each node is connected in a passive way to the bus. So this means if the node fails, all other nodes still can communicate. So it's not like when you have an Ethernet switch node where you have an integrated switch. Yeah. So it's really also if you have an in and out at a device, it's internally interconnected in a passive way.
Yes, that was IIOT was saying that one of the benefits of CAN
of course,
is that the complete controller is 100% hardware.
Yeah.
And even if the software starts working, the communication with the hardware is still working. Yeah. And that really made the change from comparing CAN with LIN or all the other communication that relies on the software running in each unit.
You're right.
Okay, thank you. Further questions? So, please.
Okay. To my mind, you presented a very balanced view on Ethernet versus CAN-FD in the automotive and for all industrial use. And now we have some discussions popping up regarding the 10 megabit Ethernet in automotive use, maybe even in non-switch topologies. What's your view on that? Does it have a chance?
Well, I'm not so into the details with the 10 megabit discussion. I think it's especially also the criteria. How will be the power consumption of this technology? Mm-hmm. What will be the price of this technology? And I would still say even if we have 10 megabit per second, we still have all the protocols that need to be executed on the CPU. So we still need to have more performance CPU with a MII interface compared to a more cheaper CPU with a CAN interface.
Okay, some additional questions? This seems not the case. So I thank you very much, Mr. Schlegel, for sharing again the experience with us. Also, again, Mr. Salzwanger.